Hello everyone, and welcome to this webinar on ray tracing for architecture, engineering, and construction in Unreal Engine. I'm your host, Matthew Doyle. Please sit back, relax, and enjoy the webinar. We will have a Q&A session at the end. Here are some of the topics that we're going to spend some time looking at today, and we're going to try to cover the basics as well as a few tips and tricks and some best practices. We'll start out with requirements and setup for using ray tracing in Unreal Engine. It's quite easy to get started. We'll look briefly at working with materials for ray tracing. We'll talk about lights and shadows, which are a very important part of doing real-time ray tracing, as well as global illumination, reflections, and translucency. We'll also take a brief look at some of the console variables, or as we call them, CVARs inside of Unreal that can help you with ray tracing, as well as some debugging techniques. Finally, with the last bit of our time, we'll briefly touch on the path tracing tool, and that's going to allow you to create very high-quality renders. And then also we'll look at the high quality media export, which can be used in conjunction with ray tracing to create very high resolution, high quality final rendered movies or still images. Okay, we'll be jumping into Unreal here in just a moment to look at setting up our ray tracing environment. But before we do, there are some things to take into consideration. You're obviously going to need a ray tracing capable video card or RTX card. And NVIDIA makes several lines of these cards. I am using an RTX 2080 Ti, which is a gaming card. And in most cases, that's going to be fine. You can use one of those gaming cards for your projects. But there are some higher level options available to you, including the Titan card or using a Quadro card instead. Now, I often get asked what the difference is between a gaming card and a Quadro card, and it's actually quite important. So if you're in an enterprise environment, you're a large company and you really need reliability and you need support from NVIDIA directly, you probably want to go with a Quadro card because NVIDIA manufactures those cards themselves, and so they have a very high quality standard, and of course you get direct support from them whenever you have issues. If you're working with a gaming card, you may not get that same level of quality, and then on top of that, you're not going to get that direct connection to NVIDIA when you need help. The other thing we'll want to do is obviously make sure we have Unreal Engine 4.25 installed or better inside of our launcher. Keep in mind that ray tracing was introduced before this, so you could use an older version, but we're going to be working with a newer version so we get all the latest and greatest bug fixes and optimization improvements. In fact, it's in 4.25 that the ray tracing solution in Unreal has been deemed as production ready. We're going to be working with a project that is freely available from Epic. If you go to the Learn tab in your launcher, and if we scroll down just a bit, we'll find the project here. It's called Arch-Viz Interior. Now this scene is fully ray traced, there's no baked lighting, and we'll be looking at it here in a moment, but it demonstrates all of the features available to us in the real-time ray tracing solution inside of Unreal Engine. And of course you'll want to create a new project with it. Before we go over to that project though, let's just go ahead and launch Unreal Engine 4.25 by itself without selecting a project, and we're going to create a new project and look at how you enable ray tracing for any new projects. Okay, so in the Unreal project browser, we're going to click on AEC. We'll go ahead and leave it as a blank project. And now here for the project settings, we're going to set ray tracing to enabled. And that's all there is to enabling the settings for a new project. And we'd simply continue from here, naming our project, picking the location we want to save it to, and then creating it. Now, let's assume that we have a project that we created and didn't set ray tracing enabled for that project, but now we've changed our mind and we want to go back and enable ray tracing for this particular project. We need to go to our settings and in project settings. And from here, we'll scroll down to platforms and it will choose Windows. And we want to make sure that default RHI is set to DirectX 12. Now let's do a quick search for ray tracing. And we want to make sure that ray tracing is enabled. And you'll see that when we do that, we need to restart our project. Let's go ahead and do that. Now, before we begin adding lights to our scene and setting up all the ray tracing effects, there are some things to keep in mind about materials. So Unreal uses a physically based material system or a physically based renderer. Everything in Unreal that's related to lights, materials, basically everything that gets rendered to the screen is tied to this physically based system. The great thing about that is that means that everything is unified. It's going to give you the correct look regardless of what lighting scenario you're in, without you having to make any kind of tweaks to the materials themselves. And it's also an easy to understand system based on real world physical laws. So really, in the old days, you would have to change things like gloss maps and things like that. But with the physically based system in Unreal, you're really just working with your base color or your albedo, as well as your metallicness, whether an object is metallic or not, and its roughness. Of course, you can work with other inputs in a material, such as normal maps or emissive or anything like that to create special effects. But these are really the three primary inputs you work with when you're working with PBR materials inside of Unreal: base color, metallic, and roughness. Now, when working with base color for ray tracing, there are some things to keep in mind. First of all, you want to avoid high contrast base color materials or textures. You want to keep them kind of low contrast so that they'll look more realistic. And another important thing to keep in mind is that in nature, there are no pure black or white textures. So, for example, charcoal is considered one of the darkest surfaces known to man, and its intensity value is about 0.02. So it's not all black. It's not just zero. Likewise, snow, considered one of the whitest surfaces known to man, has an intensity value of about 0.81. You don't want to work with the extreme values of black and white because they will make your images look less realistic. Let's jump over into Unreal and look at a quick example of that. So here in our ray trace scene, we have this black vase here. And if we go ahead and select that and bring up the material instance for it, I'm going to make some quick tweaks here to the RGB values of it. So this is our base color tint. This is the color that we're applying to it. You can see it looks very dark, very black. But the reality is we're not using a value of 0 for RGB. We're using value of 0.1 for all of those. So if I were to set this to 0, you can clearly see the difference it makes now. It is much, much darker. In fact, it's so dark, it looks very unrealistic. You don't see a lot of light bounce off of it from the ray tracing solution. So to get that to come back, to get a more realistic contoured shape, we need to bring this back up to something more realistic. So setting this to a value of 0.1 is going to make a huge difference. Now, when working with ray tracing and materials, there are some considerations that are going to help improve the performance of your scene. First of all, there are some things you're going to want to avoid. You want to avoid complex normal maps. So any normal maps that have a lot of high frequency details, little bumps and so forth, keep in mind that normal maps are going to simulate light bouncing off of little perturbations on the surface in a realistic fashion. And obviously, the more those perturbations are, the more random the light bounces would be, and therefore the more costly it's going to be for ray traced lighting. Same thing happens with roughness. So roughness is again simulating the roughness of a surface, so little perturbations that make a surface either very rough or very smooth. Obviously, a roughness with 0 would be like looking at a mirror, so very, very flat and smooth. And the reality is a mirror-like surface is actually much, much cheaper to render than a rougher surface, because we can predict very accurately which direction that light ray is going to go on a very flat, smooth surface. But a rougher surface, that's going to cause the light rays to bounce in a more random fashion, so the algorithm is more complex. And like any material, you're going to want to avoid high instruction counts. The more instructions your materials have, the more expensive they are to render. Now, there are a couple things that we can work with inside of Unreal to visualize these things, and some tools in the material editor that will allow us to make our materials more or less complex, depending on if we're using ray tracing. So let's go ahead and jump over to Unreal and look at a couple of these things real quick. So here inside of our fully ray traced scene, we can actually disable all ray traced materials to see the difference in appearance, as well as what kind of performance cost we have for our materials. And it's a global switch. It's using a console variable. So what we're going to do is we're going to hit the tilde key on the keyboard to bring up our command prompt. And you'll see it at the very bottom there of my screen. And first of all, I'm going to turn on some statistics so I can see how well my scene is rendering. We'll start out with the simple stat FPS, and that gives us our frame rate there. So I'm rendering at about 60 frames per second. And keep in mind that I'm also recording with recording software and so forth. So this is going to have an impact on my rendering time. And I'm going to bring my console back up and type stat unit. And that's going to give me the actual amount of time in milliseconds for each aspect of the rendering pipeline. So the game timing there, that's going to be CPU. Draw, that's the CPU telling the video card to render things. And GPU, that's how much time is spent on the GPU. And so basically you can see where your bottleneck is. So looks like my bottleneck is going to be in GPU time here, which is about 17 milliseconds. But let's go ahead and disable our materials now, our ray traced materials. So bringing the console back up, I'm going to type r.raytracing.enable. And we want this right here, enable materials. And I'm going to set it to 0. Now you can see when I do that, everything gets much darker because all of the materials have been now fully disabled for ray tracing. So there's no bounce lighting or anything coming off of them. And you can see my frame rate has jumped up by about 10 frames per second in this case. And my GPU time went down from 17 milliseconds to about 14 to 15 milliseconds. So it's not a huge savings. In the case of this scene might not be as complicated or complex as some other scenes would be. So we're not getting a huge savings here, but 10 frames per second can really make a difference, obviously, in some cases. So for instance, if I were to just move my camera around here, obviously the scene is much darker. We're not getting the bounced light. Likewise, over here on the TV, the screen here, it's only being affected by a cube map reflection, so we're not getting those nice ray traced reflections. Let's go ahead and turn our materials back on. I'm simply going to use the value 1 instead of 0 here. And you can see right away that the reflections are back. Now we've got nice, accurate ray traced reflections in the TV, and our lighting is much brighter because we're getting more of that bounced light coming in. Now another thing we can do to help our material performance is use a material node or expression called a ray trace quality switch. So to see how to use that, we're going to select the floor material here, and we'll open up its material instance. Inside the material instance, we'll find the parent material and open that. Okay, so you can see that this material is already making use of the node. So this node here is Ray Tracing Quality Switch Replace. And so what it's doing in this material is it's got 2 different attribute nodes here that are basically being used to create the material. So in the case of this first attribute node, make material attributes, we're piping in the base color, the metallic, specular roughness, as well as normal maps and ambient occlusion. And then that's going into the normal input of our Ray Tracing Quality Switch Replace. And you know, of course, if you want to get this node, you'd simply right-click and then type Ray Tracing, and you want it Ray Tracing Quality Switch, just like that. Okay, so this normal input here is telling Unreal to use this branch whenever we're not ray tracing. But if we have ray tracing enabled, we want to use a different branch. And so here's the second branch here, and this one is just using base color, metallic, and roughness. We don't have any normal maps piped into this one. And then that simply goes into the ray traced input here, and that will output to our final material node. Let's take a look at how we can use the ray trace switch in a material in a more practical way. So what we're going to do here is we're going to go ahead and add a cube to the scene, and then we're going to apply a mirrored texture to our cube. Now, because we have reflections on, we're getting a nice, accurate, ray-traced reflection on our mirrored surface here. But let's have a quick look at the floor here. So on the floor, you can see that we're currently rendering the normal map of our material, and we are actually a little bit blurry looking compared to the actual material on the floor here. And that's because the reflected material in the ray-traced reflection here is using a lower MIP map. So let's talk about what a MIP map is really quick before we continue. So we'll select our floor material here and then load up the instance. And from here, we're going to go down to the albedo texture and open that up. So here inside of our albedo texture for the floor, if we look over to the details panel, we can see that we have 13 MIP maps. So if I go ahead and make this a little bigger, I can actually show the different MIP map levels. So I'll go ahead and enable MIP map levels, and I'll just go through these different levels. And you can see as I go up in levels, it gets much blurrier. What's really happening here is the texture is becoming smaller and smaller. Each time the texture goes up a level in MIPS, the texture is basically being cut in half, or essentially quartered. So the highest level MIP map is your full resolution texture. And this is a technique used in game development quite often, where a texture only needs to be its highest resolution when it's up close and personal. But as it moves further away from you in space or gets smaller on the screen, the texture will automatically go down to the next MIP map because you're not going to generally be able to tell the difference. So let's go over to our material now, and let's look at how we can use the ray tracing quality switch to change a few things here. So inside the parent material, if we go down to our ray traced material and then follow the path over to the albedo texture here, you can see that the texture sample has a bias input on it. And this biased input is attached to a parameter that we're calling RT albedo MIP bias. Let's jump back over to our instance now. So inside our instance, if we look for it under scalar parameters, we should be able to find that RT albedo MIP. And currently it's set to a value of 5. That means we're using MIP map number 5. Let's go ahead and change this down to number 1. And now you can see that the texture in the reflection looks a lot more like the original texture. Now as I step up in MIPS, you'll see it slowly but surely get blurrier and blurrier. This technique is really good for saving on performance. Using a lower level MIP map means you're going to get more cache hits on your ray traces. And cache hits are basically just saved information on where the ray hit and the color of the pixel. Let's change our MIP bias to a value of 3. And now let's go back into our parent material. In the parent material, we're going to set it up so that our ray traced material is not using the normal map. To do that, I'm going to use a very simple flat normal. To do that, I'll create a 3-vector expression node, and it will change the color to blue. And now I'll plug that into my normal map input. Let's go ahead and save that now. And now you can see there is no longer a normal map inside of our ray traced reflection. So these are just a couple of techniques when working with materials that will help you to get better performance. Now there are some debugging tools for ray tracing to show different visualizations inside of our viewport that can help us to determine things like roughness. Remember, very rough surfaces are going to be more expensive to render than very smooth surfaces. So if we click on the View Mode button here, and then we go down to Raytracing Debug, you can see we have a lot of options here to work with, and we're going to pick roughness. So here in this view mode, we're seeing the grayscale representation of the roughness values of every object in the scene. So anything that is black, that's going to be very smooth surface, like a mirror-like surface. And so for instance, if we look at the TV here, obviously this would be a very smooth screen surface. So if we go back to our lit mode, we can see the ray traced reflections on that very clearly. And that's going to be a very cheap surface to render. But if we look at any of these other surfaces, so for instance the walls here, these are very, very rough. Likewise, you can see here's kind of a middle ground on the table. It's got some stripes here from the wood pattern, but very gray, so that's a very middle tone rough surface. So for instance, if I were to select this surface, and then we can go down to the material on that. Here's our wood material. And so in this case, we're using a roughness texture. Let's go ahead and open that up. So this is our roughness texture. And we were to turn off the red channel and the blue channel. This is our roughness texture here in the green channel. So you can see it's a very gray, very evenly toned gray. So it's going to be kind of a 50% roughness here on this table. And this is going to be pretty expensive to render for ray tracing because of all of these perturbations in the wood pattern and the relative middle tone of the roughness. Now that we've had a good look at working with materials when doing ray tracing, we're ready to move on. Okay, so let's go ahead and actually start adding lighting into our scene here. I've loaded up a version of the scene that has no lighting inside of it whatsoever. So if we were to go to lit mode here, we're going to see everything is just black, except for some emissive objects there. Go ahead and go back to unlit. And inside of Unreal, we have access to all of the same lights that we normally use. For baked lighting, to do our real-time ray traced lighting, we can use directional lights. For our sunlight, we can use point lights and spotlights, as well as rectangle lights, which are area lights. And finally, we can use a skylight to mimic the ambient lighting of the sky. So we're going to go over to our world settings. And then under the light mask settings of our world settings, we're going to find force no pre-computed lighting, and we're going to enable that. And this is going to make sure that we're not going to have any baked lighting in our scene. It's not going to try to bake light maps or anything like that. So we'll go ahead and hit OK. Now we could use a skylight to simulate our ambient lighting, but instead I'm going to be using some area lights in the windows. Now you can see there's quite a lot of bloom here, and that's because we need to make some adjustments to our environment's post-process settings. And we just need to make this line up basically with the window there, so we'll make some tweaks to the width and the height. Now, before we add our post-process volume, there are a few more things we need to do to any light that we add to the scene. First of all, remember, we're not baking our lighting. This is fully dynamic, real-time ray-traced lighting, so we need to set this lighting's mobility to movable. And after that, we're going to scroll down under the light settings, and then we'll go to the advanced options, and we want to make sure that cast ray trace shadows is enabled. Alright, so before we continue adding lighting, let's go ahead and add in our post-process volume. So we'll do a search for post in the place actors tab here, and then we'll drag that volume into the scene. So the post-process volume, in case you're not familiar with it, it allows you to add all sorts of effects like light bloom, exposure controls, dirt masks, lens flares, things like that into your scene. But the post-process volume is also used to enable and disable as well as tweak the ray tracing effects. Before we go any further though, let's go ahead and get our scene to kind of a clean lighting state. And the way we'll do that is under the post-process volume, we want to go through all of these options here and set them to 0. So for instance, for bloom, we'll set the intensity to 0. For exposure, we're going to set the min and max values here to 1. And then we'd want to go through all of these other options here and make sure that they are all basically disabled, such as lens flares, again, setting that to 0, and so forth. And finally, we want to go down to towards the bottom of our post-process settings, and we want to make sure that infinite extent is checked, and that's going to make sure that all of these post-process settings we're setting up are going to apply to the entire scene, whether we're inside the volume or not. Okay, so right now we're not using any ray-traced lighting or shadows. We'll get to that in just a second, but let's go ahead and add one more area light here on this window, and we'll go ahead and add in our directional light now. Now again, you can see we're getting our little preview indicator here letting us know we need to change the settings on this light as well. We'll go ahead and make it movable, and that should go away. Now in order to have ray traced shadows, this is really all you have to do is place the light in the scene, set it to movable, and make sure that under the advanced options here, cast ray trace shadows is enabled. Of course, we're not getting any bounced light going around the scene or anything like that, but we are getting the ray trace shadows. These shadows are fairly crisp, but we can adjust that very easily. If we go up to our lights options here, and we should see this option here, source angle, we can tweak this to make the shadows a lot more diffused. So I'm going to set my source angle to about 0.5 degrees. Now keep in mind this diffused effect on the shadow of the umbra of the shadow here is actually going to be softer the further away from the object that the light source is shadowing. Ray trace shadows are actually considerably cheap to use and visually provide a great effect. Alright, so now let's look at how we can bring in some ray traced global illumination as well as reflections and translucency. And to do that, of course, we're going to need access to our post-process volume. And then under post-process, we're going to go down under lens and find the rendering features rollout. And in here, we're going to find all the ray tracing options available to us. So the first option we have is ray traced ambient occlusion. In this case, I'm not going to be using ambient occlusion. We're just going to use the built-in screen space ambient occlusion. The next one up is going to be global illumination. And the global illumination option is going to allow us to get that nice bounced lighting effect. Let's go ahead and turn that on. It's going to be found under ray trace global illumination here. And then we're going to change our type from disabled to one of two options here. So first of all, we have brute force, and brute force is going to be the more accurate version of global illumination. The lighting algorithm is very accurate, but also quite a bit slower to use. So you can see I'm getting about 50 frames per second here, and it's taking about 20 milliseconds on the GPU to render this. Now I'm going to switch to final gather instead, and we can see that my frame rate practically doubles. And now I'm rendering at 10 milliseconds. Now you may not notice much of a difference. It does look slightly noisier, but this method, this algorithm is going to be the faster option, but just keep in mind it's not as accurate. It is a slightly less accurate algorithm. Now keep in mind when you're using Final Gather, max bounces and samples per pixel are really not going to do anything. They're pretty much locked to the values of 1 bounce and 12 samples per pixel. But if we were to go back to brute force, we could increase the number of bounces. But you'll see when I do that, obviously, it gets much more expensive to render. Now, obviously, we want this scene to be a bit brighter than this. We could add some more, as I said, some more rectangle lights over here to bring some light in from that direction. And there are some other things we can do here. We can increase the brightness of these two lights. So if I select them, I can change those from 8 candelas to 16, essentially doubling their brightness in effect here. And it's really nice because you can see how the lighting is just bouncing around the scene thanks to the real-time GI effect. And another option, of course, to increase our brightness is to work with our exposure controls. So if we go back to the post-process volume and then go back under lens, we'll find our exposure options here. Now, by default, it's using the metering mode auto exposure histogram, and currently we've locked the auto exposure to values of 1 and 1, locking them at the baseline state for your exposure. Now, here are some common exposure values that we could use here. These exposure values are for EV100. So that's going to be ISO 100 exposure values. And so, first of all, we have outdoor or daylight. Those values are anywhere from 12 to 15 EV. And then we have home interior. That's what we're going to be using here, somewhere between 5 and 6 EV. And finally, if you were doing something like a large window office area, you could have something from 7 to 8 EV usually for your exposure value. So in this case, we'll set our min EV and max EV both to about a value of 5. Now with our exposure value set, it gets quite a bit darker, so we're going to go ahead and increase the lighting in here. So we'll start with our sunlight, and I'm going to change the intensity from 10 lux to about 1,000 lux. And then I'm also going to change our rectangle lights here from 16 candelas to 1,500. All right, and that makes our scene much brighter. And we're going to go back to exposure. Let's go ahead and set our exposure compensation to 0. We don't need any of that. And let's just tweak our min and max a little bit more. Let's set these to about 5.5. So from here, under our post-process volumes ray tracing features, we've looked at ambient occlusion and global illumination. Next up, that's going to be reflections. So if we open up reflections here, we can see that we have the ability to change the type. Now, normally we'll be using screen space reflections. And so if we get a little closer to an object here and then go from screen space to ray tracing, you'll be able to see the difference in the quality of reflections. Now, screen space reflections are fairly good quality, but they only apply when an object is on screen. Whereas with ray traced reflections, these reflections are more accurate and always visible, regardless of whether an object is on screen or not. But there are still some dark areas, and that's because we're probably not getting enough bounces. For that, we'll open up the Ray Traced Reflections option here, and we'll look at some of these. The max roughness setting allows you to determine which objects in your scene or which materials that are reflective will make use of ray tracing. Anything below the value you specify will use ray tracing. Anything above that value will instead fall back to other reflection methods. And this is a great way to help control both performance and the reflection quality of materials in your scene. Next up, we have max bounces, which is defaulted to a value of 1. So we're only using 1 bounce to calculate reflections. To help eliminate some of these little black areas here, we'll need to bump this up. So I'm going to set it to 3. And you can see by doing that, we start to see, so if I bring this back down to 1, we're not getting the reflection between these two objects here. But when I bring this up to 3, now it's bouncing back and forth between these two objects and giving us more of a reflection. And of course, with samples per pixel, we can increase the quality. Keep in mind that increasing the samples will increase the quality, but it will also reduce your performance. And vice versa, reducing the number of samples per pixel will reduce the quality, but will speed your performance up. And finally, we can determine what kind of shadows we see in our reflections here by selecting shadows, and we can turn them off using disabled. Clearly, you can see the difference there. Or we can set them to hard shadows, which will be the cheapest option aside from turning them off. And then we can also use area shadows to get a little higher quality. However, when I turn area shadows on, you can now see that we're getting a lot of noise in our reflections here. And that's because we don't have enough samples per pixel. So we'll go ahead and turn that on. And I'm going to bump this way up to 32 samples per pixel. And clearly now we can see that our shadows are much nicer. We're not getting any more of that noise. But of course, our performance has dropped considerably. We're down to 30 frames per second now. So keep in mind, this is a way, if you want to get nice area shadows in your reflections, you can increase the quality of those get rid of some of that noise by increasing your samples per pixel. But in most cases, if your reflections are very small and most people aren't going to see that detail, just keep your shadows set to hard and then turn your samples per pixel back down to 1 and you should be fine. And so the last thing we're going to look at is translucency. So for that, I'm going to come back over to the kitchen table here, and I'm going to drag an object from the starter content pack here into the scene. What we've got here is a glass statue. Let's go ahead and reduce the scale of that object down a little bit. All right, so this is the glass statue that comes with the Unreal Starter Pack. Obviously, this glass does not look very realistic right now, but we can take advantage of real-time ray-traced translucency as well. The first thing we need to do is make sure that this material is set up to work with real-time translucency. And the first thing we want to do is on the material result node, we want to make sure that it's set to translucent, obviously, but then below that, under the translucency rollout, we want to make sure the lighting mode is set to surface translucency volume. And this is a much higher quality, though more expensive version of translucency. The other thing to keep in mind when doing ray traced translucency is that the refraction input of your material here does not affect the ray traced translucency, but instead the specular input will control that. So we want to make sure our specular is tied to a parameter, and in this case it is. So let's go ahead and create a material instance of that. I've already created one here, and we'll apply that to the statue. So this material instance is going to allow us to control that specular value. But before we can see our ray trace translucency, we'll of course need to go back to the post-process volume, go back to our rendering features, and then open up translucency, and we're going to change the type from raster to ray tracing. Now right away, without really doing anything, you can see clearly how much better this effect is. Much more accurate, much more interesting looking. Now if we open up the ray tracing translucency options here, we have basically the same options we had under reflections. We have maximum roughness, and this will allow us to control how rough a material can be before translucency will basically be disabled. And then we have max reflection rays. So if I set this to a value of 1, we can see the difference here. We don't have enough rays bouncing through the translucent surface to make it truly translucent. So we'll need to make sure we increase that. And as I increase that, you can see the difference here. Let's go ahead and add 3 rays. And now it looks like we're getting through the surface pretty well. 4 gave us a little bit more. Let's try 5. So you can see the more rays I apply, the further they can bounce through this surface and pick things up behind it. Just keep in mind it's going to get more and more expensive the more rays we have going through. Just like reflections, we also have shadow quality, samples per pixel, and then last of all, we have refraction here. So if I turn off refraction, you can see now the surface is not applying any refraction, so you're not seeing any distortion to the light rays as they come through the surface. So let's go ahead and turn that back on, and we get that nice refraction. One last thing to look at. If you recall, we can control the power of the refraction on each material using the specular input of our material. So let's go ahead and bring up the material instance we created for this. And then inside our material instance, we have the specular attribute set up as a parameter. So as you can see, as I drag the specular parameter up and down, we can see the effect that it's having on our statue's refraction. So when you're working to optimize your scene while still maintaining a high quality bar, here are some things that you should keep in mind. First of all, interior spaces are actually more expensive than exteriors. So all of these same techniques we just looked at work pretty much the same if you're doing a large exterior scene. But it's actually going to be generally cheaper because if you think about it, what's happening is an interior space, especially with real-time GI, ray trace GI, you've got the light that comes in through your window and then it's going to bounce around however many bounces you have it set to, and that's going to be expensive. Whereas with an exterior space, the light rays are going to come in from the sun, they're going to hit a surface, and most of them are going to bounce right back up into the atmosphere. And so they will be just going off into space and they won't have any more effect on your calculations. So again, same basic techniques, but actually cheaper. Remember to avoid using overly complicated materials. They are going to be more expensive. And also remember to keep your roughness and normals under control because normal maps and roughness are going to increase the algorithm's render time for real-time ray tracing. And that's because smooth reflections are simply much cheaper to render, because the calculations for that are a very easy to predict thing. So as far as expense goes, in order of expense, just keep in mind that real-time GI, as well as reflections and translucency, those are going to be your more expensive options to use. Keeping in mind that Unreal is a hybrid ray tracing solution, and so you can pick and choose the ones you want to use that have the most visual impact while having the least effect on performance. And that's going to depend from scene to scene. If you have a scene that has a lot of reflective objects in it, you're going to want to use real-time ray traced reflections. Likewise, if you have a lot of translucent objects, you'll probably need to use that. And in real-time GI, remember, you have two options. You can go with brute force, which is more accurate but much slower, or you can go with the final gather solution, which does a really good job of approximating the full ray traced algorithm. Now, we did look at console variables today a little bit. There are some other options that you have available to you to help you with your performance. I've listed a few good ones here. Some of them are good for modifying your performance, and some of them are just good for debugging. So for instance, we already looked at raytracing.enable materials. We can also enable and disable all ray tracing effects entirely using the second one here, and that's going to be r.raytracing.force all ray tracing effects. Let's jump into the scene and have a look at that. So if we bring up our console with tilde and then type r.raytracing.force all ray tracing effects, and we set that to 0, all ray tracing is now off. So we're not getting any bounced light, any ray traced reflections or translucency, and ray traced shadows and so forth. And so let's go ahead and turn that back on now. Take note of the performance there. And we can see with everything turned back on, we only lose maybe 5 or 10 frames per second in this case. So it's a good way to quickly turn those off, see what your performance is like without them, and then turn them back on, and you can see the difference. And then last of all, another one we can look at is going to be max ray trace distance. And each of the options has this available. So if we do r.raytracing. Let's say global illumination, and then do max ray distance. And if we set this to something really low like 10, you can see what happens there. This is obviously way too low of a value, so you start to get some splotchiness and some noise there. So we want to make sure that we have that set to a high enough value to give us a good quality look while maintaining a good performance rate. So you can go through here and tweak these max ray distance settings for each effect. So just keep in mind that by increasing and reducing the max ray distance, you can affect the performance of your scene, and so you want to basically find the sweet spot where everything still looks good while maintaining as much performance as you can. And then the other thing we'd want to talk about briefly is your debugging tools. We've already looked at how to bring up stat FPS as well as stat unit. And in stat GPU, you're going to find all of the ray tracing passes here and how long they're taking on average, max, and minimum in milliseconds. So we can see we've got our primary ray pass here for ray tracing, taking about 2 milliseconds on average. Below this, we have GI, reflections, we've got our ambient occlusion, and so forth. So here you can see exactly what your bottleneck is. Now there's two last things I'd like to briefly talk about today, and that's going to be getting rendered outputs of your ray trace scenes. Obviously, this is mostly for real-time ray tracing, so you have real-time 3D visualizations. But you can render out movies and screenshots at a high quality. So if we go back to our post-process volume, the first option available to us is going to be found under our rendering features, where you find the ray tracing options, and that's going to be the path tracer. From here, we can control the maximum number of bounces and samples per pixel for the path tracer. Now, the path tracer is essentially a renderer just like V-Ray or other options. So this is not a real-time solution. It's not something you'd want to run in a real-time visualization. I've moved to a different bookmark here, and we're going to do a quick path trace render. To see your path trace, you'll need to go up to the View Mode button and then select Path Tracing. And we can see the path tracer begins to render, and as it gets better over time, obviously it will look less noisy. Now, if we want to render out the path tracer, we're going to have to use the high-res shot console command. So I'll go ahead and bring up my console command here and type high-res shot, and then we'll go with 1920 by 1080. Now, the problem here is it'll take the shot, but as you can see when it does, it starts all over with the path tracer. So let's look at the result of the high-res shot. Okay, so the high-res screenshot has been saved in our project's Saved Screenshots Windows folder. And we'll go ahead and open it here. and you can see that it's quite noisy. Basically, we got a render when the path tracer first started rendering. So in order to remedy this, we need to set a delay on the high-res shot. So to do that, we'll bring the console back up, and we're going to type high-res, and then what we want here is r.highres screenshot delay, and then we'll need to specify the delay that we'd like to use. So for instance, I'll go ahead and type 10. And from there, we'll go ahead and fire off our high-res shot command again. So let's check out the second screenshot. It's not actually much better. So here's the original shot, and here is the newer one. So just a little bit better. But obviously, the longer we give the delay, the better the screenshot's going to look. Let's go back and give it a longer delay. This time we'll set it to 100. And we'll fire off our shot again. All right, let's look at our new shot. And we can see it's getting much better. The noise is much more reduced now. And if we walk back, we can see the change over time. Your second option for creating high-quality outputs is going to be the new high-quality media export tool. So inside of Unreal, we have our sequencer tool, which allows us to set up camera animations and so forth. And the new high-quality media export tool allows us to take those animations and render them at a very high resolution using ray traced quality. It provides you with a very highly configurable export tool that allows you to create presets that you can save. And then what it does is you can create images as high as 20K, I believe, in resolution. And the way it does that is it literally cuts the image into pieces or tiles, and then those tiles are able to be put back together after being output into the final full high resolution image. So let's have a look at how to use the movie render queue. We're going to find it under the window menu and then cinematics, and from here movie render queue. Now we can create multiple renders and basically queue them up and have Unreal render them out one at a time. To add a sequencer cinematic to the queue, the first thing we'll need to do is click the green button that says render and then pick the sequence we'd like to use. So as you can see, the first item in our queue here is archviz Cine Master. This can be changed using the drop down. Then we have the settings that will be used for this render, and then the output location. Let's go ahead and set up all the settings for our render now. To do that, we'll click on this unsaved config link, and this will bring up the settings window. By default, our render is going to be set to render as a JPEG sequence using deferred rendering, and then here are our basic output settings. Now, if we wanted to render in a different type of format, we could simply click on the settings button and then go down to output and choose something else. For instance, we could use PNG here. Now, if we don't want to render out the JPEG, simply select it and then turn it off. From here, we'll need to go to our basic output settings. So let's go ahead and set our output resolution to 4K. That's going to be 3840 by 2160. Now, Unreal can output this resolution natively. However, we can take advantage of the new high-resolution tiling renderer by going to the Settings button and choosing High Resolution. Let's look quickly at some of these options. Tile count will allow us to specify how many tiles to use, both vertically and horizontally. Let's go ahead and change it now to 2. This will result in 4 tiles. Keep in mind that the size of a tile should be no larger than the maximum texture size supported by your video card. Using tiling does not currently support several features inside of Unreal. Some of those features include light bloom, screen space effects, as well as auto exposure. So if you're using auto exposure, you're going to want to go into your post-process volume and change that to manual camera exposure and then readjust all of your exposure settings. Our overlap ratio is currently set to 0. You can set this to between a value of 0 and 0.5. A higher value here means there will be less errors along the tile edges. Just keep in mind that a higher overlap ratio will take longer to render. Setting this value to 0 will be much quicker. However, each tile will be more prone to errors. Let's go ahead and set this to a value of 0.1. Now, obviously there are a lot of other options available to us here for our settings, but due to time, I'll leave these for you to investigate. From here, we can save this preset by clicking on the Presets button and choosing Save as Preset. Let's go ahead and create a new folder for it. I'll save the preset in my Cinematics Presets folders, and I'll just call this My Preset. Okay, and then we can hit Accept, and our preset is set up for our render. Now we have the choice of rendering local or remote. Rendering locally will allow us to render essentially like play in editor, and this will allow us to actually preview the render as it's rendered. Render remote will launch a separate session of Unreal that will render in the background. And this option allows us to even create our own render farms that can attach to the movie queue. Okay, so let's go ahead and render locally, and this will bring up the render preview window. So we can see the total number of frames, and currently we're at 8 of 1492. We also have the amount of time that's passed, as well as time remaining, and it's letting us know what the current state is of the rendering pipeline. And this is the overall, or the entire sequence, while the information on the right refers to any specific camera cuts within this sequence. This sequence contains 11 camera cuts. We can see that we're currently on cut number 1, and that we're currently about 38% done with rendering. So we'll go ahead and let this run in the background, and we'll come back in just a minute to have a look at the frames. To make things go a little faster, I changed my output resolution to 1920 by 1080. But this is still 4 tiles rendered separately by Unreal, and then Unreal automatically puts the tiles back together. So we can see as I move backwards in time here through the different images of my sequence, the result of the renders. Now this is a tad bit noisy, but keep in mind we're rendering at 1920 by 1080, and I really didn't do anything to improve the anti-aliasing or any quality settings. There are a lot of things we could do to get rid of this noise, such as working with the denoiser and so forth, but due to time constraints, we're just going to go ahead and leave this here today. Thank you for being part of the webinar today on ray tracing in AEC for Unreal Engine. If you'd like to learn more about using Unreal Engine, please be sure to stop by unrealengine.com/online learning. You'll find tons of great courses there on everything from your first day in Unreal to advanced topics like materials, effects, post-processing, and all sorts of other topics. All right, so we're going to go ahead and open it up to Q&A now. Hope you enjoyed the webinar, and thanks for being here.